Hey, Chloe, it's great to have you here for this new episode. Today, we're diving into something pretty fascinating. Levitation microsystems. Tiny devices that can actually suspend micro-sized objects without any physical contact.
Yeah, Liam, it's a really cool topic. I mean, the idea of making things float, like really float, at the microscale, using electromagnetic forces, is just, well, it's kind of magical, isn't it?
Absolutely. And what's exciting is that these levitation microsystems, or L microsystems, don't just float things for show. They eliminate friction and wear, which means devices last longer and can work in harsh environments, even in a vacuum.
Right, and that's because they balance gravity with electromagnetic forces, creating a stable suspension. So no mechanical contact means no friction, which is a big deal for precision and durability.
Exactly. And thanks to advances in microfabrication, permanent micromagnets, and magnetic polymers, these systems have become practical and efficient. They're already being used in sensors, actuators, micromotors, gyroscopes, and even microfluidics.
And the potential goes way beyond that. Robotics, medicine, optics, biology. It's a multidisciplinary playground.
So to get a handle on this, it helps to understand how these levitation microsystems are classified. The key is the type of force fields they use and how they maintain stability.
Yeah, and that brings us to Earnshaw's theorem. It's a fundamental physics rule that says you can't have stable levitation using only static inverse square force fields, like static electric or magnetic fields, without some kind of active control.
Right, so that means if you just try to levitate something with a static magnetic field, it won't stay put unless you have sensors and feedback loops to keep it stable.
Which leads us to the two main levitation modes. Active levitation, where sensors and feedback maintain stability, and passive levitation, which relies on static or dynamic fields without feedback.
And based on the force fields, levitation microsystems fall into several categories: electric levitation, magnetic levitation, diamagnetic levitation, superconducting levitation, inductive levitation, and hybrid systems that combine multiple forces.
Each has its own perks and challenges. For example, electric levitation uses electric fields to levitate charged or dielectric microobjects, but it needs complex active control.
Magnetic levitation uses permanent magnets and coils to levitate microobjects, while diamagnetic levitation uses materials that weakly repel magnetic fields, like pyrolytic graphite, to levitate tiny droplets or beads.
And superconducting levitation exploits the Meissner effect, where superconductors expel magnetic fields, enabling stable levitation at cryogenic temperatures, around 90 Kelvin.
Inductive levitation is particularly interesting. It uses alternating current coils to induce eddy currents in conductive microobjects, which then generate magnetic fields that repel the coils, causing levitation.
And hybrid systems combine these forces to optimize performance and stability, which is pretty clever.
Speaking of electric levitation, it was first demonstrated back in the 90s, suspending microdiscs and plates using tuned circuits.
Yeah, and active electric levitation can stabilize silicon rotors spinning up to 74,000 revolutions per minute. That's pretty fast.
Definitely. Applications include accelerometers and even containerless high-temperature processing of materials, like suspending zirconium spheres heated to over 2,200 degrees Kelvin.
But electric levitation requires precise gap control and complex active feedback, which can limit scalability.
Magnetic levitation microsystems use permanent magnets and coils to levitate microobjects. There are prototypes levitating magnets and microswitches, with forces in the micro to millinewton range.
Diamagnetic levitation is fascinating because it can levitate tiny droplets and beads without contact, using materials like pyrolytic graphite. These systems can achieve ultra-high quality factors, making them promising for resonators.
Superconducting levitation systems, while limited by the need for cryogenic cooling, offer exceptional stability and frictionless suspension, which is great for micromotors.
Now, inductive levitation microsystems really caught my attention. They use AC coils to induce eddy currents in conductive microobjects, which then repel the coils, causing levitation.
The first prototypes levitated aluminum discs a few hundred micrometers in diameter, but early planar coil designs had a big problem. They generated a lot of heat, up to 600 degrees Celsius.
That's wild. 600 degrees is enough to melt or damage the device.
Exactly. The breakthrough came with three-dimensional microcoil technology developed around 2010. These 3D coils allow many more windings in a compact space using only 2 photolithography masks.
And that reduces energy dissipation and operating temperatures dramatically, down to around 60 degrees Celsius.
Plus, integrating polymer magnetic composite cores into the coils concentrates magnetic flux, further reducing the required current and heat.
So 3D coils enable stable levitation, rotation, and even transportation of micro-objects with much better efficiency.
Racetrack-shaped 3D coils add degrees of freedom for micro-object movement, which is pretty neat.
Experimental measurements confirm improved stiffness and stability in these systems, which is crucial for practical applications.
But heat dissipation remains a major challenge. Even though 3D coils reduce heat compared to planar coils, the heat is concentrated in a small volume, so thermal management is critical.
And stability is tricky too, especially because of Earnshaw's theorem. Without active control or hybrid force fields, stable levitation is impossible in static fields.
Vacuum environments make it even harder because they reduce damping, which normally helps stabilize the system.
That's where polymer magnetic composite cores come in. By guiding magnetic flux efficiently, they reduce coil current and heat generation by nearly half.
And hybrid levitation microsystems combine electric, inductive, and diamagnetic forces to improve stability, reduce noise, and enhance control.
Hybrid systems enable quasi-zero stiffness control, meaning the system can be very sensitive and energy efficient.
Applications include gyroscopes, accelerometers, micromirrors with wide scanning angles, and microtransporters.
Hybrid designs also allow bistable actuation and pull-in mechanisms, expanding functionality.
Speaking of applications, microaccelerators levitate and propel microobjects along coil tracks using sequential electrode activation.
Microgyroscopes use spinning rotors levitated electromagnetically to measure angular velocity with reduced friction and noise.
Microaccelerometers levitate proof masses between electrodes for precise acceleration sensing with adjustable stiffness.
And micromotors and switches offer frictionless, contactless actuation at the microscale.
Microfluidics benefit too, with contactless manipulation of tiny droplets and particles.
The potential future applications in robotics, optics, chemistry, medicine, and biology are really exciting.
On the modeling side, analytical models use Lagrangian mechanics and Maxwell's equations to describe the coupled electromagnetic and mechanical dynamics.
Eddy currents induced in levitated objects are approximated by discrete circuits, which makes the modeling manageable.
Stability theorems show that dissipation or damping is essential for stable levitation.
Symmetric and axially symmetric designs simplify modeling and improve stability.
Experimental stiffness measurements validate these models, which is reassuring.
Now, noise and performance limits are critical, especially for levitated gyroscopes.
Mechanical thermal noise arises from Brownian motion and limits gyroscope sensitivity.
Levitated gyroscopes can achieve lower mechanical thermal noise than vibrating gyroscopes because of frictionless suspension and vacuum operation.
Johnson noise, or electrical noise, also limits resolution.
Position stiffness, how strongly the rotor is held in place, critically affects noise and resolution.
Inductive gyroscopes have lower stiffness and better noise performance than electrostatic ones, but currently achieve rate grade rather than navigation grade performance.
Increasing rotor speed and inertia improves noise performance.
The scale factor, or sensitivity, depends inversely on position stiffness.
Achieving tactical or navigation grade performance requires extremely low stiffness and high quality factors.
Experiments confirm that 3D microcoils with polymer magnetic composite cores reduce operating temperatures and required currents significantly.
Hybrid actuators demonstrate bistable behavior and angular positioning with pull-in actuation.
Microaccelerators successfully levitate and propel micro-objects with stable linear motion.
Microaccelerometers show adjustable stiffness and precise capacitive sensing.
Analytical and quasi-finite element models accurately predict pull-in voltages and displacements.
Looking ahead, fabrication challenges remain, especially integrating advanced materials and achieving precise control.
Hybrid systems combining multiple force fields are promising for overcoming limitations.
Further development of soft magnetic layers and polymer composites will improve efficiency.
Expanding applications in robotics, medicine, optics, and biology is anticipated.
Improving vacuum operation and thermal management will enhance device lifetime and performance.
So to wrap up, levitation microsystems are a fascinating blend of physics, materials, science, microfabrication, and control engineering.
They offer frictionless, contactless suspension and actuation at the microscale, with broad applications and exciting future prospects.
And the advances in 3D microcoil technology and hybrid systems are key to making these devices practical and efficient.
It's a field that's really pushing the boundaries of what's possible at tiny scales.
Thanks for joining me to explore this, Chloe.
Thanks, Liam. It's been a pleasure diving into this with you.
And